one sort of fun way to understand if you know how volume integrals work is to try to take the same integral and interpret it in different ways. Uh, this is actually an important point because many people look at an integral at this point. You know, they learned about area, they learned about volume, and they'll say, okay, is this integral? Is it a volume integral? Is it an area integral? Well, there aren't really volume and area integrals. There are volume problems that you can solve with certain integrals by setting them up. That doesn't mean that the same that doesn't mean that the same integral can't be the answer to a different type of problem, maybe a different type of volume problem, or maybe the same integral that answers a volume question also answers a different area question. So let's take a look at part A, and with reference to the integral that's up here. So we have the integral of v equals 0 to 1 of pi times x to the fourth dx. So let's ask, if this is the volume of a solid of revolution, obtained by the disk-washer method, then where the axis of revolution is the x-axis, describe the solid. So what we know is that if I actually have, let's say, I have some function y equals f of x, and I revolve it around the x-axis on the interval 0 to 1, thereby forming a solid that looks like this by the disk method, we know that the volume would be given by the formula integral from 0 to 1 pi times f of x squared dx. So we can actually use that fact to figure out what f of x must be in this instance. So we have comparing this part here with this, we set up the equation pi x to the fourth equals pi times f of x squared. Cancel a pi and get that x to the fourth is equal to f of x squared, or f of x equals x squared. Okay, so we now have the function, so we can write out a description of the solid, and I'm just going to zip through that description. Okay, so we have a good description of the solid when interpreted this way. So now what we want to do is part B, where we want to take the same integral and try to interpret it a little bit differently. So let me get a little more space here. So if this is the volume of a solid whose base is bounded by the x-axis and the curve y equals f of x and the line x equals 1, so that's x equals 1. So the base, just to be clear, is going to be this region of the xy plane. And we know is the cross sections are squares that lie across the base perpendicular to the x-axis. So what we want to do is describe what this region is. So realize that if this was the first example by slicing we did, and if we have squares where the side of the square lies across the base like that, perpendicular to the x-axis, then remember that length of the side had a length of f of x, so this was the side, and the area of one square was equal to f of x squared. So the integral that we would have gotten for that solid would be volume is equal to the integral from 0 to 1, because we'd be proceeding in this direction, giving thicknesses like that, so we'd go from 0 up to 1 of f of x squared dx. So that means that we can now equate the integrand in the given integral, pi x to the fourth equals f of x squared. So that means that f of x is equal to the square root of pi x to the fourth, or square root of pi times x squared. So basically a parabola. So what we can see is that, actually I'll put all that up in a minute, is that what we have is we have a base that looks more or less like that, y equals the square root of pi times x squared, and it's bounded on one side by 1, and we have the sides of squares lying across the region like this. I won't try to draw them so that they come out of the page, but you've already seen what those models look like. So the same integral can be interpreted in various different ways. In fact, it shouldn't surprise you that I can interpret this same integral as just this could be the area under the curve pi x to the fourth on the interval 0, 1. There's no particular reason that that's not a valid interpretation.